So welcome back to the workshop. So after 3 nice talks, we have 3 other nice talks too. So let's start. So we have next speaker is Robert Heath. So he's here. So Robert is a distinguished professor at North Carolina State University, and he's a worldwide expert on wireless communication, in particular millimeter wave communication. He has been actively working on joint radar and communication for particularly for vehicular application. And today he will deliver a talk on his proof of concept platform you named JCR70, right? So using 70 gigahertz band to make all this integrated sensing and communication practical in real world application scenario. So you should be able to share the screen, I guess.
Yep. Okay. Just coming on here. Done. Okay. So you see everything?
Yes, we see.
Okay. Perfect. Thank you.
Go ahead.
Yeah. So it's great to be here virtually. I'm dialing in from Raleigh, North Carolina, where I moved this past year, just in time for no teaching and due to COVID. And so it's been an interesting time getting to know colleagues when you're not even allowed in the office. So I'm happy to be in this session because I want to talk about some of the work we've been doing for a number of years related to joint communication radar, which is part of this paradigm of joint communication sensing, which is now getting a lot of interest in the context of 6G. And I want to start off with, first of all, just a bit of a summary of our vision about sensing and communication and why we think this is important for 6G. And this is part of this center that we've kicked off at North Carolina State University. It's led by Nuria Gonzalez-Prelchich and myself, and composed of 15 great faculty that are distributed in areas of circuits and antennas, signal processing, communications, and then networking and applications. And so we've got a good group here that has the right expertise to work on the kinds of problems like I'm going to talk about today. And then our interest in this started, I would say, at least my interest in maybe 2012, 13 timeframe. Started collaborating with some folks in civil engineering, looking at some problems in transportation, as well as started working with some automotive companies, looking at millimeter wave communication for vehicle-to-vehicle applications, as well as some potential low frequency in radar. And so that got me, interested in what was a big area of, I guess it was on maybe PowerPoint engineering for 5G, was on this vehicular application, which didn't really make it in and is now something I think that's going to be there more for 6G. And so one of the things that we have seen the last number of years has been this trend of an explosion of sensors on vehicles, and the sensors are there so that the vehicle has better situational awareness. It can use that information to make decisions on its own. And I'm showing vehicles here, but this is just an example of a trend that's happening in many application verticals around automation. So this could be factory robotics, agriculture, urban air mobility. Robotics in general all has this common theme that sensing is used to understand the environment, to make decisions. And what we think that's going to happen is that these sensors slowly are going to be pushed more and more onto the infrastructure itself. And so that could mean that base stations are equipped with not just cellular communication, but also radar, LiDAR, other forms of communication, cameras as well. And that information can be processed at the edge. And so these automation applications, instead of all the computing being done in an autonomy fashion in the vehicle, it can be done at the network, at the edge, if latency is a concern. And the sensors are not just there, they might be there to support automation, but one line of work that we have investigated, in particular, my colleague Nuria has been leading, has been this idea of using sensing to aid communication. And she's got some nice work on where the radar measurements used in a different band are used to derive site information about the communication channel. And this idea proposed, and I think she proposed it 7 years ago now, but has been tested, measured, and so it's an interesting idea that shows how information derived from a sensor can aid communication. So communication's role is maybe to exchange sensor data, but the sensor can help the communication to exchange that data better. So kind of a intriguing shift in the way of thinking about communication and radar together. And then this fits in more broadly with our vision in 6GNC, where we're looking at new technologies, disruptive applications, and smarter infrastructure. And joint communication sensing is part of that infrastructure, but it's enabling the applications, and it's feeding in to the new technology as well. So if you use sensor data, it can become much easier to configure a terahertz MIMO communication link, because maybe you don't have to search over as many beams as possible. So this is something that we think is quite important, and we've been excited about ever since that early work on the vehicular side. Now, before I start talking about some of the prototyping challenges, I was just going to give a little bit of a perspective on why joint communication and radar. And so we started this work. This was one of my former PhD students had started a company and then wanted to step back and look at maybe doing something else. And this Dr. Robert Daniels, he went on to become part of Phaser, which was sold, and he's now has another startup now. But he came back to UT, where I was for a little while at that time, and had this idea that we could use maybe the 802.11p, which was part of this dedicated short-range communication standard for vehicle-to-vehicle communication. Maybe we could also use that for radar. And this dates me a little bit, because in the US, DSRC is basically dead technology. It's been that vehicle-to-vehicle connectivity has been replaced by cellular. But at the time, it wasn't clear that was going to happen. And so I had this idea of essentially just using this Wi-Fi type waveform for radar. And people had been looking at that for gesture recognition and other applications, but we hadn't seen it too much work on it being used to detect another vehicle. And the basic idea is, you're talking to a vehicle, that vehicle's maybe exchanging information with you, and then you use the echoes of that signal to see where the vehicle is. And that gives you important site information about, the range and velocity, and that can also make the link more secure. So we built this, had this idea, did a lot of simulations. We built it and tested it. And one of the things that we found was that it worked, which was great whenever you come up with an idea and you build it. We also found that if you look at this picture here, that it really worked best when we had these big fat patch antennas. And then, we come back to Toyota, say, hey, look, we have this great solution for you. You can use the cheap DSRC radio for radar, and then just, put these big fat antennas on the front of the car. Wasn't really a good selling point from an industrial design perspective. And so then in some later work, we studied this with more realistic assumptions using the tiny little antennas that are normally on the fin of the car, and the performance wasn't as good. And that's one of the things that one of the things that always reminds me why prototyping is important, is that it gives you a practical sense of whether the things that we're doing, how and where they might apply. So I think the theory is great because it tells you, it gives you a good description of everything. But then, if when you plug it into the system with the realistic parameters, and well, maybe it just doesn't work like expected, and maybe you achieve the theoretical performance, but the theory is just not what the application needs. And that was what we found here. So we were pretty close to the Kramer-Rao bound, but then it turned out that it just wasn't good enough for the application we needed. And the reason was the bandwidth. And so another line of work that we had started also around 2014 was to look at millimeter wave communication signals also for radar. And so this was, now keep in mind, this is well before millimeter wave was, 5G was standardized and millimeter wave was part of it. So that was just when millimeter wave is kicking off. And the thought process here was, well, if radar is better at millimeter wave and we also can do communication at millimeter wave, maybe we can just do both at the same time. And so we started with the 11AD waveform, which was the only commercial waveform at the time. And the nice thing about it is that the preamble structure has repeated Golay sequences, which have really good correlation properties and are independently used in radar. And so we started this work, eventually published it in a longer paper with my colleague Nuria, and then a PhD student, Preeti Kumari, who's since graduated and is now working at Qualcomm, who led this, and then Junil Choi was my postdoc at the time. And so we found that actually this, in principle could work really well. 11AD has a lot of bandwidth. And then if you're talking to the car in front of you, you could listen to the echo. And so, and in principle, everything seemed to work well. One of the main assumptions we were making, though, was that we didn't have any self-interference. And so we wanted to put a system together and then tried to study a little bit better what the implications of that might be. And also to understand just in general relationships between the MIMO configurations that we could use, the resolution of the data converters, and the eventual performance. And so that led us to the work I'm going to talk about today. I will skip that slide there. So I'm going to tell you about this prototyping that Preeti did over a period of several years. It's one of the challenges of doing prototyping versus theoretical work is that it just tends to take longer. Maybe I'm not working on hard enough problems in theory, and that's why they don't take so long, but it just seems to take forever, and then can be demoralizing for the students who want to graduate in a timely fashion, and they just get stuck for reasons that are related to getting a piece of equipment shipped. These days, just getting it in time. It took 14 months for me to get my equipment from UT Austin to NC State, and I don't think it was necessarily due to COVID, but it certainly contributed. It wasn't being shipped around the world through the Red Sea and the Panama Canal, et cetera, but it took a long time. So what we found, so we started this in 2000, probably 17, 18 timeframe. And at the time, there wasn't too much in the way of millimeter wave communication prototyping capability. Most of it was derived from equipment that came from National Instruments. So Nokia had a high visibility prototype on this. And so we ended up building our prototype off of equipment from National Instruments, and I'll explain it a bit more up in the E-band at 73 gigahertz. There were some other prototyping efforts that were using 802.11ad cards and either using that standard or had some hacks to get in a little bit further and to do things with 11ad, but we couldn't get enough access to the digital parts that we needed to do radar very well. And so that didn't really work for our purposes here, but it was good for what that was used for proof of concept. And then the other dimension that we wanted to explore was this area of MIMO configuration, low resolution. And then we found that there was some MIMO radar prototyping, software-defined radar, which we had been using in my lab from INRAS, the radar book and the radar log, where we could vary resolution. But then we couldn't do the communication. So we could study radar and radar performance without communication. We could study communication, we didn't have radar, or we could do something with a communication, but it was more an application. So we couldn't do the radar and we couldn't do the physical layer processing. And so then the net of it was that we couldn't find an existing solution. So we decided to put something together ourselves that would allow us to do these studies. And the type of work that we wanted to do is we wanted to have a configuration, something like as follows, where there's a transmitter and a receiver, and that the transmitter side, which we're calling here the source, there's self-interference, and it's also listening to the echo of the transmitted signal to do radar processing. And so we wanted to be able to do both at the same time, receive the communication signal, analyze the performance, as well as simultaneously receive the radar reflection, analyze the performance, so that we could come up with plots where we could talk about the performance at the same time. And then we wanted to be able to vary the resolution of the ADCs and have a different number of RF chains. Varying the resolution of ADCs is the easiest of all of them, because if you have a high resolution one, you just throw the other bits away. So that wasn't too hard. It was the bigger challenge was figuring out how to make all of this work for MIMO. And then we ended up using a waveform that came from the software that we had from NI, which was close to what's in 11AD using the single carrier mode. So it's not quite what's in 5G now, but worked quite well. And what we ended up doing was we ended up, because we could only afford to buy a certain number of RF chains, we ended up virtualizing on one link and using, so by sliding one of the antennas into multiple positions, we were able to get effectively a larger dimension MIMO system at the expense of not being able to do the Doppler type estimations in real time. So this is the CISO setup that we started with here. CISO, but we have a communication transmitter, a radar receiver, and a communication receiver. So it's not quite CISO, but there's no MIMO in each of the transmitters or receivers here. And so we used typical high-end components that could allow us to do 2 gigahertz of bandwidth for each of these RF chains. We used horn antennas because we didn't have the fully digital capability at that time. And this was before some of the more commercially available digital, like not analog beamforming solutions that you could get for millimeter wave were available. We had some in my lab, but they didn't have good enough phase control to be used for radar. So this is the kind of setup that we had. So we had, the transmitter and the 2 receivers, and then we wanted to do more. So the idea that Preeti and I should mention, was working with Amin Mezgani, so professor now in Manitoba. They were working on this idea that, okay, so what we would do would be, we would come up with a way to step the location of the transmitter. And so they using one of these photography sliders where you can put a camera on a slider and they use it for picture filming and various things to track something. You can get a small one digitally controlled. So they put in this case, the transmitter on one of those and then step it through various positions so that you can effectively have MIMO antenna at different places. And of course, you're not getting the mutual coupling, and you're making some assumptions here, but we were able to get that. And then we had a fixed receiver location. And then on top of that, we put our friendly automotive radar, which is also operating is at the 77 gigahertz band and uses 100 megahertz of bandwidth and uses, we were able to make our own comparable radar processing algorithms. So we were able to compare back to back. So we could do communication, radar with the comm signal, and compare the performance with the off-the-shelf radar. And then to do the comparisons in the real world, one of the things is you need a benchmark, because how do you know it's working? So what we use to determine if it's working is we use these things here called corner reflectors, which are used in experimental studies to act as like a point reflector. And so you can just measure the location of that corner reflector. And then when you do your radar processing algorithm, you can see, how well were you able to estimate the location. So the point reflector allows us to get that ground truth that we can use to validate the work. And then one of the things I should mention is that, so we ended up, we did all of this in like a MISO configuration, but we used reciprocity to effectively do things in SIMO. And the reason is that it was, we wanted to keep the same, we wanted to keep something here fixed. And so it just ended up being easier to fix the receiver than it was on the transmitter side, because otherwise we'd have to also be moving the radar as we moved the receiver, the baseline radar. So that was the other, I think, main assumption we made, but the reciprocity is not, I don't think that's a significant one here. So I don't have too much time left. I'll try to wrap up to give you an idea of some of the things that we did. So without going to all the details, we wanted to compare the performance that we could achieve using different algorithms. And so we ended up using like a standard FFT type radar processing approach, and we compared it with something smart using a GAMP algorithm that's exploiting the sparsity in the channels to do better parameter estimation. So, and then we've used GAMP in the past on problems related to low resolution compressed sensing. And so this was going to allow us, this was going to give us an algorithm that we could use for both communication, channel estimation, and radar. And we could use it with variable resolutions, and it would be better than something that is typically used in the radar community. And then we used as a backup this INROS radar book as a ground truth. Now, this is not a commercial, it's used as a commercial radar chip, but we are doing the processing. So we're not taking like a Delphi radar that has common filtering and target detection, tracking, all of that. We're just using this as a software defined radar, and we're using the same kinds of algorithms to compare the performance. And that approach, that supported 4x8 with 12-bit ADCs and roughly 100 megahertz of bandwidth. And our approach, we were using in the end a gigahertz of bandwidth. And then here's some of the setups that we used in order to get some variable positioning. We did use that target on a vehicle. This vehicle is this big, is not as big as a regular vehicle. We did do some estimation with a bicycle. The bicycles, we don't really have a perfect ground truth because we don't know which parts are reflecting, but we get, it's better. It's different than the multiple point reflectors. And we also took the equipment outside. Main limitation, we couldn't really study Doppler effects. And then I'll give you, I think just in 1 minute, maybe I have left 1 or 2 minutes. I'll just give you an idea of the kinds of results that we were generating with the prototype, and then that'll be it. So what we were doing is we were looking at range azimuth type plots. And then this is what we could achieve using a traditional bin based. You're looking at the energy in a range azimuth bin. It's kind of like a periodogram type estimator. And then we saw things like, well, there was the self-interference effect, there was an effect from the wall, there was the target. And then when we fed all of this into this EM Bernoulli-Gaussian GAMP algorithm, we were able to really, because of that sparsity, we were able to pull out the location of the target much better. And this worked also with the baseline radar book too, just for comparison. You can see that the two graphs here are different in part, basically because of the bandwidth. The radar book has 1/10 of the bandwidth, so it doesn't get as good of a resolution, but it still is able to estimate reasonably well. And so we did some studies of the performance with number of bits by taking the data, throwing the bits away, and running the algorithms again. This is an example where we did this with, what is this here? This is the 2 corner reflectors. So we put 2 corner reflectors close together. One is bigger and smaller, so they don't reflect at the same rate. And you can see here that the higher bandwidth and with the better processing, we can separate out the 2 corner reflectors. And so this, gives evidence to this idea. And then the 30 steps here, this is like 30 antennas. And then this is 29 antennas with the 29 virtual antennas with the radar book. So it's a kind of a comparable setup. And then this is with the bicycle. So we don't have a ground truth here. I mean, we know roughly where the bike is, but so you can see here that with the better signal processing, you can pick up some of the specific points of reflection off the bike. And then the resolution gives you, much more of the bike. Bikes are important. I used to bike a lot. And also when a car and a bike come together, the person on the bike tends to be the one that dies. So I think, bikes are generally quite interesting for that point of view. Now, of course, I just drive, so maybe it doesn't matter so much. But that's some of the examples there. And then this was one of the examples of being where we were looking at the channel and comparing the communication channel performance. I think I'll skip that. So the net of it is that it's important to put together these ideas, joint communication and sensing, put everything together, and try to prototype it as much as possible. I mean, we're at the point where 6G is a good 8 years away from deployment at least, and probably we have another 5 years of doing serious research. And I think this is the time to do serious research on it. I mean, we can say, okay, joint communication sensing is going to be a part of it, but we need to do both theoretical and practical research to figure out how and where it's going to be useful. And I think some of us may be jumping the gun a bit and just kind of jumping in without thinking more carefully. And I think this is the good time to do that. We leverage the excitement around communications to do the both the theoretical experimental work. And there's a lot of work to be done. I mean, I think just on the waveform design, there's many trade-offs that can be had, because generally you can make the waveform work better for radar, but then you sacrifice communication dimensions. There's a lot of ways to work together with multiple radars, multiple transmitters, using multiple different distributed training symbols. We did that in some other work where you can get better Doppler estimation. In general, like working with MIMO, canceling self-interference, making it work well with spatial, temporal ranging, looking at hybrid architectures, going to higher frequencies at above 100 gigahertz, and then just more experimental validation. I mean, what I showed you is very simple. I mean, it'd be great to do this with a fully digital millimeter wave or sub-terahertz setup, and I think that would be the next step. And so that's what, if I had the money, that's what I would do in my lab now, would be to build something much more sophisticated. And then just to conclude, I mean, I talked here about joint communication radar, but remember, radar is one of many sensors. We have a lot of other work where we've used position information for millimeter wave beam training. We were working on that for 5 years. We've used LiDAR for beam training, use other information. So it's one of many sensors, but I think it's one that is particularly relevant for communication because they're using such similar frequency bands, and so the information can be derived from one for the other. I think it's a very natural thing to do. So I'll stop there. Thank you for the opportunity.
Thank you, Robert, for your nice talk. We have time for one quick question, if the audience has some. If not,
it's definitely very clear.
Yeah, you convinced all of them.
Or too fast.
I have a quick question. So you had a different setup. Mostly here you presented indoor scenario, right? One with small car and the one with bicycle. Or
yeah.
For both model, you consider which standard model, which is like a point target or extended target model, and how they are realistic in this setup?
Well, you can see the I mean the model, the algorithms are looking for, you know, significant points. I mean, that's the way all the radar is working, right? Is you're normally you're interpreting something here, and then there's an algorithm on top that tries to say, okay, you know, is there a target there? Is this one target or two targets? You know, so there's many different signal processing tasks there. What we were doing just to simplify the process was using this approach that exploited sparsity, so that the sparsity essentially just helps us filter out the noise in the signal. So, you know, that's why this and this, you can see that the two targets here on top of each other. But here that, you know, it would be harder to discern, like, it's like pulling out, it's just sinusoids and noise. I mean, you've got here two sinusoids and there's a lot of grass there. And then over here, I mean, yeah, we don't really know what points here are coming from which parts of the bicycle, but there's definitely a lot of structure there. And if you were to replace the radar with a LiDAR, you would see the same thing. You would see a point cloud. You don't see, you know, you don't get an image, you get places where the light comes back. And so using this kind of processing, we get a data structure that is already being used in automation, because I mean, LiDAR is heavily used in automated workflows as well. So I think all of this ends up being a pretty good assumption, but, you know, really to test the performance from a radar point of view, you'd have to integrate this in the more complete radar system with the target detection, the tracking, and all the other parameters. And you know, that requires better hardware and much more money to test it.
Yeah. Yeah, I'm asking because bicycle has just a very small reflecting surface than usual vehicle or car. And
But this is amazing. So you can see the bicycle, right? The bicycle's 1.5 meters, right? So you can see, I mean, this is a great result because this will allow the algorithms to discern that this is a bicycle versus this blob here, right? So I can't imagine what the machine learning will do, but to me, this is good, not a bad thing, because it means that there's multiple points, and then presumably we could train a good neural network that could learn that that's a signature of a bicycle, and we have to,
Nice.
send that information up. So,
Yeah, great.
thank you.
Thank you very much. So maybe we can move on. So if audience, you have some other question, please ask question on chat. And if Robert can stay for some minute, then he can maybe directly answer on chat.
Yeah, I try to answer them on the chat. Thank you.
Yeah, thank you. So